Current sensing is a rather interesting topic in power systems. As we can see here, we've got Danisense and they're showing off some rather interesting current clamps, from the small to the very, very large. But wait for it, there's more, because we've got this bad boy. Now, before we dive into all of this stuff, I've got a good friend here from Danisense, and before we dive into the cool stuff, just tell the audience who you are, what you do, and what you like to do in your free time.
Oh, in my free time, okay, good.
If you have any.
Okay, so hi everyone. So my name is Loic. I'm the sales manager for Danisense. And Danisense is a Danish company and we are dedicated for current measurements. But not the usual one, a special one which is extremely accurate, but we will come back on that. And for my free time, what I like to do, fishing. I really enjoy
Awesome.
fishing. So.
And I might have just had a small revelation, like a mind blow. Is it called Danisense because it's Danish sense?
No, it's Danisense, which is Danish sensors, which is
This is Danish.
the
Oh, right, okay,
of those.
okay, yeah, brilliant. I thought, oh yeah, I see where it's coming from. Fantastic. So, as we can see here, as we said earlier, current clamps. And the size of some of these are absurd. This one here, size of my fist, probably actually bigger than my fist. So, my first question is, where on earth do you use this?
Yeah, excellent point. So this product has been specifically designed for high power product because we can measure up to 4,000 amp, 7,000 amp peak, and there is more and more requests for large aperture measuring small current. So typically state of health for battery, supercap.
And charging systems.
Exactly, correct.
Right. But what charging system has a cable that size? Like it's massive.
So it's typically for marine application, boat, ships, trucks, where you need a huge power, because sometimes you can go up to 3,000, 4,000 amp.
I guess a lot of these cables have quite thick insulation, shield.
Correct.
Right.
That's
So it's not like it's the whole thing's copper. It might be like
no, you're right.
The copper might be like that big, but it's got a huge. Yeah, okay, that makes sense. So you need these to be sensitive to pick up that field because the smaller the cable, the harder it is to.
Exactly.
Yeah.
And which is important for this application more and more, it's to measure accurately small current. So when you have to measure 20 amp, 50 amp on this size, you need to be super accurate.
And when we say small currents, you know, like you say, if the nominal current is 4,000 amps, you might want to be able to measure 1 amp, which is hard to do at such high amperage.
You get it. Yeah. Exactly.
Is that to do with the magnetics being like saturated at sort of those currents and stuff? Is it anything to do with that, or is it what makes it hard to measure an amp when you're dealing with 4,000 amps?
The real challenge is the linearity, which needs to be really high, and the offset. And on top of that, the offset drift as well.
So over time, it gets magnetized, the core it saturates, becomes harder to measure small changes and stuff. So
exactly.
So might be a really stupid question. Do these only work on AC or do they work on DC? Then they work on DC. No,
both.
AC.
AC and DC.
On DC as well.
Yeah. Right.
How do you? Because I know
specifically DC, by the way.
That's interesting because I know with like transformers, you need AC to change the magnetic field, so you can measure the output changes for the current. So how do you do it for DC?
So this is a technology called fluxgate.
Nice.
And the principle is pretty easy. So you have the magnetic core, you saturate and desaturate it, and then you get a very clean signal and let's say symmetrical signal.
So you drive the coil.
Right, exactly.
To measure.
Right.
I guess because if it's DC, it has a fixed magnetic field. So the way that those magnetic fields interact with each other, oh, that's genius.
Okay, and then when you have a perturbation from the other external field, you change the nature of the signal, and this is the way you are rebuilding, let's say, the value of the current.
Because correct me if I'm wrong, but like if you have an AC wire, you just have a simple like coil around it,
correct.
and you can just see the induced voltage,
It's
and that's
transformer
proportional.
Effect, yes,
But in this case, you have to actually modify the core itself
correct.
to be able to see how the DC current is changing it. So that is honestly amazing. That's absolutely amazing. So we've looked at this one here. Marine applications, big charging systems, huge currents. But tell me what's going on with these smaller ones.
So for this smaller one, it's a mix of this kind of small products are used for the power supply. So typically MRI scanners or particle accelerators, they need a very stable power supply output.
Sorry, did you say particle accelerators?
Yes, so typically the CERN.
Oh, that's cool.
Okay, so when you have the particle running,
Oh, yeah.
it's guided by the magnetic field.
Yeah.
If the magnetic field is not under control, the particle is going anywhere.
Yeah.
So you need a super stable
Traveling
current.
at 99.999% speed of
Exactly
light.
correct.
Trying to get two protons to hit each other.
Right. So
Incredible.
this is the reason why they need this kind of high accurate
And these
measurement.
things are making sure that those magnetic fields are perfect.
So this one is special because it's a residual current.
Right.
So the idea is here you put the let's say the three phase, and you can monitor if you have any leakage somewhere for safety reasons.
Because if they're balanced, there'll be nothing at all.
Normally you should have zero,
Ah.
but you can track very small current, and when you have the drift, then you need to switch off your installation. We can do that with DC and AC as well.
That is, and again, with the DC, you're modifying the field to see
That's
if
the
it's being
same
affected.
principle for everywhere.
That is honestly amazing because I didn't realize you could measure current, DC currents with a coil like that. I always thought it had to be AC, but you can basically put AC on it.
Correct.
To see how that's really amazing. What is quite interesting is that I find it funny how this one has the tiniest little connector for measuring the output voltage and the currents. But what is interesting for these ones, you've got a DB9 connector. So
Right, we do.
So tell me a little bit more about what's going on here.
Yeah, so the reason why we selected this one, it's because this is a little bit more for test and measurement. So you plug and unplug all the time, but you need to make sure that it's really
Secure,
well secured.
shielding.
Exactly. And on top of that, you have power supplies. We are also integrating, I don't know if you are familiar with TEDs, technical electronic data sheets. It's an EEPROM inside, where when you plug the instrument, you will load all the data. The turn ratio, the nominal current, the offset drift, and so on.
Oh, that's so cool.
And you can set up that in your instrument automatically. So that's something we can do that with this connector as well.
Jim, that's the first time I've ever heard that.
Yeah, but I would say TEDS, it's existing
my
for
God.
20 years. But it has never been in the, really implemented in a current transducer.
That's the first time I'm hearing about it. That's amazing. The idea of an EEPROM inside components to give you the data on that component in the first place.
So it's a plug and play. You plug it.
Does
the
that mean
instrument
that
recognizes it.
each individual, when they get manufactured, the EEPROM has slightly different data for that specific coil? Like let's say you manufacture 1,000 of them, because they're all going to have slight variations.
Correct.
The EEPROM would be when you test it at the factory, you would get all its characteristics and then put that into the EEPROM. So each one will be slightly different.
You could do that, yes, because we can do also a calibration,
Yeah.
and we put the data which is specifically to this transducer.
That
You're
is
right.
and I guess in places like CERN, that's going to be important, where you need to make sure that if you've got 10 of them, that one might be slightly different, so you need to be able to account for all these slight variations.
Correct. This is what they do calibration as well.
Yeah,
You're right.
so it makes them smart, effectively, to a degree. It makes them smart, and
Correct.
it's just honestly so cool. So interesting setup here. And are those flat wire inductors, or are they regular?
No, it's just a current which is going around.
Yeah. And then what's going on the screen here? Because this is all quite
Exactly.
interesting.
And what we would like to demonstrate here,
Yes.
because products here are pretty nice, but
Yep.
most of the time in the instrumentation and test and measurement, they are requesting something which open and closed.
Yeah.
So this is why we developed with the same technology this clamp here.
Oh, that's a man's clamp. Look
Okay.
at that.
And if you look on the screen, if you are using the normal probe, you see on the screen it's moving. So there is a sensitivity of the measurements, because if
Oh,
I'm
yes, I
moving
can
here,
see.
or you
And-
can see the numbers.
And to be clear, while it may not look like much, that if you're doing highly accurate work, that's not good enough.
Correct.
Yeah.
If it's moving, it means that you have a sensitivity.
Yeah.
With our equipment, for efficiency measurement, power measurement, they need to be extremely accurate. And if I move here, you see,
No
the red
change
line,
at
no
all.
change at all.
And just if you move this and I'll move this one at the same time, you can see that
Oh yeah,
that's
sure.
the blue one going.
That's the correct, the green one.
Yeah. Oh.
Okay,
Is that green? I thought it was blue.
Oh, what's going on here?
There you go. I thought that was. Oh yeah, maybe
This
it's
is the
green.
green
yeah.
one.
That's the green one. See, that's
Correct.
shifting around a lot, and then
Yeah.
here comes the big one.
And if you do the same, you can move it.
Absolutely nothing at all.
Correct.
Okay. Over there. There we go. That's perfect. Yep.
Now
Oh,
you- now you
it keeps
can-
getting.
you can
Yeah,
move
take it
it.
off. It keeps getting in the way. There we go. That's better. Yeah, absolutely nothing at all. That is amazing. Look at that. Those peaks are not changing at all. And so, and I suppose what you're really trying to show here is that anyone can make a current clamp. Only you can make the current clamps.
In a certain sense, yes. This is our DNA. We really are in the high precision.
If you want a real serious current clamp, capable of doing particle physics, high accuracy current measurements, boats charging, particle manipulation, this is the place for you.
Exactly. You are more than welcome. But you're right. This is the place for that.
Fantastic. Now, just before we wrap up this video, I've got one more question for you.
Yep,
for the audience who are watching this episode, if they want to get involved with these solutions, what would you recommend that they do?
If they want, sorry?
If they want to get involved with these solutions, what would you recommend that they do?
They come to us, of course.
Come to those guys. And that's it. Fantastic. Well, all I can say is thank you ever so much for having us here today. It's been an absolute pleasure, honestly.
Pleasure to you too.
All right, this one.